Good afternoon. During the lecture today, I will present the second fundamental form in local coordinates. So let S be an oriented regular surface and let sigma define on new open set of R2 with values in V subset of S be a surface patch and let N denote the orientation and assume that sigma is compatible with the orientation. I want to be sure that it's clear what this means. N denotes the orientation, means that N is a choice for the unit normal field to the surface, and sigma is compatible with orientation, means that the normal unit field that you can obtain this way coincide with N. So this is the meaning of the sentence sigma is compatible with orientation. Now let's recall what we did in the past for the first fundamental form. So we define the functions E, F, G as follows. E is the length of sigma u squared. F is the inner product of sigma u with sigma v. And G is the length of sigma v squared. And we wrote down the formula for the first fundamental form in local coordinates, which is F1 equal to E du squared plus 2F du dv plus G dv squared, where du means the derivative of the function that maps uv to u And similarly, dv is the derivative of the function that maps uv to v. We also saw the following identity. If Q is a point of U, and we use the fact that TQU is nothing but R2, then if X is a point of TQU, F1 QX is d sigma Q applied to X length squared. Now we want to do something similar for the second fundamental form. In order to do this, we define three auxiliary functions: E, F, G, and we use the notation, the simplified notation according to which n replaces n composed with sigma, and I drop everywhere the point Q where I'm evaluating these functions. So Q dropped. What is the definition of these three new functions? E is given by the inner product of sigma u with n. F is given by sigma uv multiplied with n, and G is given by sigma vv multiplied with n. Now I want to observe that there are alternative expressions for E, F, and G. Precisely, E is also equal to negative n u sigma u, but this coincides with W, the Weingarten map evaluated at sigma u multiplied with sigma u. This is equal to minus nu sigma v, and this is also equal to minus nv sigma u this is also equal to W sigma u sigma v, which is also equal to W sigma v multiplied with sigma u. And last, this one, this is also equal to minus inner product of nv sigma v, which is equal also to W sigma V multiplied by sigma V. Let's prove, for example, the first one. The proofs of the other identities are very similar. So if you want to prove the first one, just observe that this inner product is always 0. Why? Because sigma u is a tangent vector and then is orthogonal to the surface. So this means that n is orthogonal to any vector in TPS, where P is a sigma q. And what happens if we differentiate this identity with respect to the variable u? We get 0 equal, now maybe I should write this way, n sigma u so I have to use the formula for the derivative of a product, and I get nu sigma u plus n sigma uu, and from the fact that this is equal to 0, I get immediately this identity. Instead, the second identity follows from the fact that by definition W of V is minus D n V, and remember that the symbol n u is nothing but then the derivative of n composed with sigma along in the direction with respect to the variable u. So you have to just use the chain rule, and you will get immediately that this is equal to the derivative of n evaluated at sigma u. And this is nothing but then minus W sigma u multiplied by sigma u, and there is a change of sign because of this sign in front of the inner product. Okay, now we are ready to give the definition of second fundamental form in local coordinates. So the second fundamental form in the local coordinates u, v, also known as the second fundamental form of sigma. So SFF means second fundamental form, is the expression F2 equal E du square plus 2F du dv plus G dv square Similarly with what we did for the first fundamental form, I want to prove this proposition. So if Q is a point of view, X is a vector in TQU which can be identified with R2, and P is a sigma Q, then we have that F2 at point Q evaluated at the X. This is the following thing. Where what is the meaning of this symbol? I want to recall it here. Okay, let's prove the proposition. So suppose that X is a vector of component AB, then this implies that du of X is equal to A and dv of X is equal to B. This is something we already used, so I think I can skip the proof of these two identities. Then what is the sigma Q of X? This is d sigma Q of A1 plus B E2. That is A d sigma Q E1 plus B d sigma Q E2. That is A sigma U plus B sigma V. And now I will drop everywhere the letter Q. So what happens if I now evaluate the right hand side? And now I use the bilinearity of the inner product and the linearity of WP, and I get A Now I use the formula for the maybe it's a good idea to keep these identities on the blackboard for a moment. So now I use the definitions of EFG in terms of Weingarten map. So you get that this is exactly E, this is exactly F, and this is exactly G. So I can write a square E plus 2F, 2ABF plus B squared G. And now I use these two identities because I can write now E du x squared plus 2F dux dvx plus g dv square x. And this is nothing but F2 evaluated at Q of x. So the identity is now proved. Okay, now I want to recall the following fact. The second fundamental form, second P, is the quadratic form associated to WP, the Weingarten map, and we already showed in the past that they provide us with the same information. If you know the second fundamental form, then you know WP, and if you know WP, you know the second fundamental form. Now, what we proved is to write down the second fundamental form using E, F, and G. So what it is natural to ask is it possible to find a formula for WP in terms of E, F, and G? It's natural because we were able to answer a similar question for the second fundamental form. The answer is provided by proposition 4.17, which says that the matrix whose entries are W11, W12, W21, W22, that represents WP with respect to the basis sigma U, sigma V of TPS is given by this formula. Okay, let's make one remark before presenting the proof of this formula. So this matrix is expressed in terms of not only E, F, G, but also in terms of the coefficients of the first fundamental form, capital E, capital F, capital G. We can ask ourselves what are the conditions to be satisfied in order to have a matrix depending only on the coefficients of the second fundamental form, E, F, and G. The answer is when sigma U, sigma V is orthonormal, that is E equal G equal 1 and F is equal to 0, then the matrix which represents the Weingarten map reduces to E, F, F, G. But this is a very special case because in general this is not true. How to prove this formula? We need to use the identities relating the coefficients E, F, and G with the Weingarten map. Precisely E equal W S U multiplied by SU Then I use the fact that this is a matrix representing this map, this linear map, so I can write W of sigma u as W11 sigma u plus W21 sigma v multiply sigma u, and by linearity I get W11e. Maybe let's write something more, sigma u plus W21 sigma v sigma u, that is W11e plus W21f. Okay, if you do the same with f equal W sigma u, maybe let's write also p here to be precise, sigma v, you can prove that this is equal to W11f plus W21g. From this identity you can find that this is equal to W12e plus W22f, and g is given by W12f plus W22g. Okay, now let's think of this 4 equation as a system of 4 linear equations and 4 variables. W11, W12, W21, W22. In order to solve these equations, we will not use a 4 times 4 matrix. I mean, you would like to write this as a E, F, F, G equal E, F, F, G, but we will use a trick we will write this equation as E F F G equal W11 W21 W12 W22 multiplied by EFFG. This is possible because here you have W11 W21 and also here W11 W21 W12 W22 W12 W22. The unknown is this matrix here, which is exactly the matrix we are looking for. So we can get W11, W12, W21, W22, multiplying both sides by the inverse of this matrix. And if you make the computations, you will find exactly this formula. Since this is the a matrix which represents WP, then I can use it to compute the Gauss curvature and the mean curvature. The Gauss curvature is defined as the determinant of this matrix, and some computations gives that this is equal to Eg minus F squared divided by capital E capital G minus capital F squared. Instead, the mean curvature, which is defined to be 1/2 the trace of this matrix, is equal to 1/2 E capital G minus 2 F capital F plus G capital E divided by 2 Eg minus F squared. Now let's see some examples. Let's erase also this part. So let's consider the graph of a function, and our goal is to compute the Gauss curvature and the mean curvature using these two formulas. So let U be an open set over 2, and phi a smooth function. Then the graph gamma of phi is a regular surface which is covered by just one surface patch. And this surface patch is given by this formula. We already computed sigma x, sigma y. They are given by 1, 0, phi x and 0, 1, phi y. We also computed the orientation associated with this surface patch. This is a sigma x cross product sigma y divided by the length of the same vector, and this is given by phi x, minus phi x minus phi y 1 divided by phi x squared plus phi y squared plus 1. The coefficients of the first fundamental form are then given by E equals sigma x squared. This is 1 plus phi x squared. F is a sigma x inner product sigma y. This is given by phi x phi y. And G, this is sigma y squared. It is given by 1 plus phi y squared. In order to compute E, F, and G, we need to compute sigma xx, sigma xy, sigma yy. So we have sigma xx equal 0, 0, phi xx, sigma xy equal to 0, 0, phi xy, sigma yy 0, 0, phi yy, and this implies that E, which is given by the product, the inner product of sigma xx with n, is just phi xx divided 1 plus phi x squared plus phi y squared. F is the product of sigma x, y, and n. So I get phi x, y divided by square root of 1 plus phi x squared plus phi y squared. And G is given by the inner product of sigma yy with n. So you get phi yy divided by square root of 1 plus phi x squared plus phi y squared. And now if you use the formula for the Gauss curvature, you will find that this is equal to phi xx phi yy minus phi xy squared divided by 1 plus phi x squared plus phi y squared power 2. Instead, the formula for the mean curvature is a bit more complicated. And this is one. Next example. Is the one of surfaces of revolution. So suppose that gamma t is the regular curve having this form, that we rotate around the z-axis. So and we will suppose that gamma is parameterized by arc length. Which means that x prime square plus z prime square is equal to 1. And when I write prime, I mean the derivative with respect to t. In this case, the surface patch is this, sigma theta t equal xt cosinus of theta, x of t sinus of theta, z of t. And if q is an arbitrary point or coordinates theta t, then sigma theta at q is a minus x sinus of theta, x cosinus of theta, 0. So here I dropped the independent variable t, and sigma t at q is x prime cosinus of theta, x prime sinus of theta, z prime. The coefficients of the first fundamental form are given by these formulas. And the vector, the normal vector n induced by the surface patch sigma is given by sigma theta cross sigma t divided by the length. This is given by z prime cosinus of theta, z prime sinus of theta, minus x prime. Please observe that this formula is simple, relatively simple, because of this hypothesis. In fact, if you make computation, you will find out that sigma theta cross product sigma t squared, this is x c prime square plus x prime square, and this is equal to x square because of the fact that zeta prime z prime square plus x prime square is equal to 1, which is exactly what we wrote here. Now, in order to compute the coefficients of the second fundamental form, we need to compute sigma theta theta, sigma theta t, sigma tt. It's possible to prove, okay, let's maybe write down all the formulas. Sigma theta theta equal minus x cosinus of theta, minus x sinus of theta, 0. Sigma theta t is minus x prime sinus of theta, x prime cosinus of theta, 0. Sigma tt, this is x prime, x second, sorry, cosinus of theta, x second sinus of theta, z second. And if you multiply these three functions by n, I mean you consider the inner product of these three functions by n, you will get E equal minus x z prime, f equals 0, and g equal x second z prime minus x prime z second. The Gauss curvature is a very simple formula, minus x second over x. Also in this case we use the fact that x prime square plus z prime square is equal to 1, otherwise the formula would be more complicated. And the Gauss curvature, sorry, the mean curvature this is given by this formula. If you want, you can also try to find the principal curvatures. Now, in this case, it's easier than usual because k is equal to Eg over capital E, capital G. This is true because f is equal to capital F equal to 0. And for the same reason, H, the mean curvature, is 1/2 Eg plus Ge over Eg. And this can be written as 1/2 E over capital E plus G over capital G. Now, you know very well that K is K1 plus times K2, and H is 1/2 K1 plus K2. So what are the values of K1 and K2? Simple. They are E over capital E and G over capital G. So this implies K1 equal E over E and K2 equal G over G, capital G. This is equal to minus Z prime over X, and this is X second Z prime minus X prime Z second. In the general case, this is not true. And if you want to find the values of the principal curvatures, you have to use the following formulas. Then you can use these two formulas. They follow from these two identities. You have to ask yourself, what are the numbers k1, sorry, k1, k2, whose product is k, and whose average is h. The answer is k1 is given by this formula, k2 is given by this formula. Okay, the next result I want to present provides the visual interpretation of F2, second fundamental form. Precisely, we have proposition 4.21, which says that if Q is a point of view, P is sigma Q, where sigma is a surface patch, X is a vector tangent to U at Q, then the normal component of the difference sigma Q plus Tx minus sigma Q. So this is the normal component of this difference. This is approximately equal to T squared over 2 F2 at Q evaluated at X. In this formula, the error satisfies the following property: the limit of Et over T squared is 0 as T tend to 0. Let's prove this proposition. In order to prove this proposition, we suppose that Q has coordinates given by U0, V0. X is AB, where A is PUQ of X, TVQ of X. And now we use the Taylor approximation of second order of sigma at Q. In other terms, sigma Q plus Tx, this is equal to sigma Q plus T maybe let's save time and say, let's say that no, I changed my mind, so let's write everything plus T squared over 2 So this is what we get. So what happens if now we multiply sigma Q plus Tx minus sigma Q with n? We get that if we drop the error term, we get only T squared over 2 A squared sigma U Q plus 2AB sigma UV Q plus B squared sigma VV Q and P. The reason why there is no term involving this summand is that this is a tangent vector A sigma U Q plus B sigma VQ is orthogonal to NP because this is a tangent vector. Now let's use this fact, this identity here, and we get T squared over 2 duq of x squared times E at Q. This term comes from the product of sigma UUQ and N plus 2 duq x dvqx multiplied by f this term originates from the product of this term and n plus dvq x squared gq, where this term originates from the product of sigma vv and n. But this is nothing but then t squared over 2 second fundamental form at q evaluated at x. Now let's make a picture. So suppose that this is the open set U over 2. This is the point Q, and this is the direction X, and this is the size the value of t. Then what is the image by sigma of q plus tx? Let's suppose at this point here sigma q plus tx. So suppose that this is the surface S. This is a point P equals sigma Q. No, it's not a good idea to write this here. P equals sigma Q. This is TPS. This is the normal vector. Let's suppose that this is d sigma qx, and this is sigma q plus tx. Then this result says that the normal component of this vector, which is this height, this is approximately equal to t squared over 2 f2 q evaluated at x. Okay, let me check how much time I have. Okay, I think we can stop here for today. Thank you for your attention.